It's called Dealing with. Okay, now it's recording. Hi, everybody. My name is Michael Mesquita. I live in Norway. And I've worked with Morgan and Michel, but also Lydia for some time now. And this presentation will focus on dealing with uncertainty and looking at how numerical weather prediction simulators work. Just note that I'm using the word simulator, and that's how statisticians like to call climate models. And so because I'm focusing on uncertainty and it requires measuring statistical properties of climate models, so that's why I've chosen the word simulators instead of model here, just to let you know. Just a little bit about ourselves. Lydia, your picture is not here, but Lydia has joined us also and has helped quite a lot with some of the work we're doing with the Worf model. I met Morgan, by the way, at the University of Alaska Fairbanks. We went to grad school there, so there's a picture of Morgan there as well. And then later we started working with Michel, and we have a project going on at the moment where we are creating a book about modeling and especially about regional climate modeling, downscaling, and the Worf model. Michel and Morgan and Lydia, feel free to say something, okay? So, and stop me whenever you want me to. Since 2013, actually, Morgan and I, we created a website called m2lab.org. And from where we have been offering online courses for some time now. And we've trained actually many people, researchers, professors, students all around the world. And actually this was earlier this year, more than 1,500 people, and we have actually more than 1,600 people we've trained throughout the years, and especially a big focus on regional climate modeling with Worf, but also R. And in addition to that, other aspects of statistics we've considered as well. We have a publication describing the online course. It was a collaboration with Oxford University, our friend Peter Walton at Oxford, where we describe about a comparison between the course we offered and the course that Oxford offered. And this was published in BAMS in 2016. So it's a very nice reference about how to teach online and teach something very complex as climate modeling online. So, but before we start talking more in depth about downscaling, so there's this question about why are weather and climate simulators useful? So I'm going to just give two examples of applications in my own research. One is this paper that we published in 2016 with colleagues from Norway. This was actually a popular science paper of the original paper. So it was a summary of the original paper that we published. And I was invited some years back by some ecologists who studied seabirds, and they wanted to know what happened to the seabirds in the 1980s. As you can see, there is a time series plot here. It's difficult to see, but you can see that a huge drop in the number of seabirds in one winter. It was 1986-87. In that winter, almost the entire colony of seabirds disappeared. And so some research later, they found out that there was a lack of food, meaning lack of fish, because these birds, they live at sea during the winter, and they can withstand, low temperatures in the winter in northern Norway. So this is northern Norway. They live at sea during the wintertime. But why did the entire colony, almost the entire colony, died? They are called common guillemots. And so they called me and asked, can you help us find out if there was a climate component that would help explain the deaths of these seabirds? And so I went there, and I actually worked in the project with them for some years. And we were able to find out what happened, that there was a climate component, a weather component in that case. And basically, it's a long story, but just making it short, the seabirds, even though they can withstand low temperatures, but not extreme temperatures. So at that time, we found out that there was a polar low that passed by, and the polar low it can freeze structures like ships, for example. So the seabirds didn't have enough food. And in addition to that, we had a high pressure system that was sitting there during the wintertime, which made the conditions even colder than normal. And then we have the polar low going and freezing everything. So we believe that helped explain even more, helped put together, let's say, what happened to the seabirds. But definitely the lack of food was the main factor. But weather in that winter definitely helped kind of, unfortunately, kill many of these birds. It was a detective story. I remember we had to analyze reports from the time of veterinarians talk, what they described about the birds, and ships that found them dead at sea. And so it was a very interesting story. That's why the name of this article was Cold Case, because we had to open and see how they were killed. And here we definitely had to use data from models to be able to answer these questions. So climate simulators, yes, they are necessary because it helps us even reconstruct things that happened in the past. Another application, it's part of my research work as well. In this case, there was a group of ecologists studying moths. And at one time in the year, these moths, they spread. So basically going with the wind, let's say, and spreading from one area to another area and going to different trees. So these ecologists, they go to these trees and they capture the moths and they try to understand, especially looking at things like genetics, for example, and how they disperse. So for this study, I did a lot of simulations using the Worf model to try to see where the flow of the air was going, because here in this part of Norway, you have fjords. So fjords, you have the mountains, and then you have sea going through these mountains there. And it's a very, very complex topography. So using data from global models is not enough because the resolution is not good enough. So you have to go down to higher resolution to be able to understand. So we use both reanalysis data, and I did simulations with the Worf model as well to understand in detail what was going on. And so the ecologists use these data to then be able to understand more about what was going on. And this was the paper as a result here. So just two applications of the importance of climate simulators, not just for us to understand climate change like the COP26 conference, but also, or for weather prediction, but also for other applications such as something that we call climate ecology, how climate affects ecological systems. This was new for me, I have to say. I had never worked with ecology before, but when I started working with the groups, I had to study a little bit about ecology, about seabirds and etc., moths, to be able to do that work. And it was very exciting, I have to say. I really enjoyed working with ecologists. But now, another question that it always intrigued me is, can we trust simulators? And we know that people say, that models are not perfect, right? We know that models are not perfect. They're just trying to describe nature somehow, but they have errors, but they are useful. And we know weather prediction, how things have changed, right? Before it was hard to trust weather prediction, but then with time, improvements in the models and so on. So we have very good predictions. Let's say 7 days, maybe even 15 days, you can get some very interesting, good predictions going on there. And then when you go to seasonal prediction, then things get a little bit fuzzy, but there's always improvements. And then we also have longer predictions of several years that helps us understand and make plans for the future. But again, there is a lot of uncertainty. So here, in this plot, we're just trying to show that climate has different scales, both time scales in this case, or size scales. For example, from dust devils, something at a very small scale, to the monsoon system, for example, in India or other places. So there are different scales here. And for each scale, there are different ways to simplify the equations of motion, or other equations, for example, from thermodynamics, that would describe the system, that would model the system. For instance, if I'm going to study the monsoon, it doesn't make sense to take into account things like friction, because friction would make more sense if we're studying smaller systems like dust devils or turbulence in general. So by simplifying the equations, we can make models run faster, but at the same time, when we simplify, we remove things that would help improve the models. So the simplification adds errors, of course, but again, the question is, how uncertain are these simulations? So again, models are still useful, but we need to make approximations. And whenever we cut something from a model, there are ways to try to represent what we cut. And these we call parameterization. So we can build auxiliary models that run a little bit faster to help explain things that we removed. We're going to see a little bit about that in a little while. Another thing that we need to consider is chaos. So basically, if I start a weather model and I use start initial conditions, for example, I start the model at midnight from 3 days ago and run forward in time, or if I start at 6 a.m. 3 days ago and run forward in time. So because I start these two simulations at different times, we have different initial conditions. And because of that, the solutions will be different. And this is because of chaos, because of the way the equations, as we integrate them forward in time, they can deviate from the true solution. And the more we run forward in time, the more it deviates in time as well. And this was discovered by Edward Lorenz and others in the 60s, looking at how these equations would deviate, which means that weather prediction is a chaotic system because of the types of equations that we use. And because of that, we will not have true solutions in a way. They will deviate. But there are other things also to consider. And another thing to consider is about numerical instability. We know that computers or calculators, they cannot take into account the full range of digits from the number system, right? And because of that, we introduce errors. And these errors, as we are keep integrating in time, they also can accumulate. So we also have some numerical instability going on there. So there are ways to control this chaotic behavior in weather prediction systems. And the Worf model, which is the model we're going to talk a little bit in a while, there are ways in the Worf model of controlling that. One way is called nudging, which means that as you integrate forward in time, you make a correction to the model and you try to correct whatever you're doing so that the solution is not going to deviate that much. This helps improve. There are other things, other methods that can be used as well to diminish that. In terms of numerical instability, there are ways of discretizing the equations that would make this integration forward in time be more stable. So there are a number of things that can be done to make it better. This is a paper that we published in 2017 in Nature Climate Change, where we look at the uncertainty. So basically, if you look in the left-hand side, there is this blue area. This is basically the space of solutions that that you could have from a model. So if you think of that blue area as things in nature that you're trying to represent, let's say temperature, and then you want to see temperature in the future, and basically the blue area represents the probable states in the real world. This is the real world, the blue area. Think of temperature or rainfall, for example. The problem is that if you look at the yellow things, the first figure to the left, the yellow drawings represent what the global models are sampling. Because we don't have a lot of resources, so people have to ask for help from different institutes around the world and ask them, please, can you run a global model and give us your simulations to create an ensemble, a large number of simulations. This is what the IPCC report does. The problem is that you cannot, because there are not enough computational resources available, you cannot sample the whole space of the real world. So basically, the simulations that are provided simulate just part of that. And then the resolution of these models is not good enough. So what you do, you have to use a regional model like Worf Model to find information in higher resolution at the local place where we are living, at the point where we are living, for example. And because that is expensive computationally, there are projects that ask different institutes around the world to run different models and provide their simulations. And again, you're trying to sample as well as much as possible, but it doesn't cover the whole region. So ideally, what we wanted would be the figure B, still to the left-hand side of this slide, the figure B, where you would sample a large area of the reality. That would be amazing, because then you would measure the uncertainty of the models in a much better way. So there are ways of trying to do that, but still we need to improve that. So this paper is about the importance of improving the types of experiments we run, and the importance of collaborating with statisticians to find out smarter ways for designing these experiments. Here's an example from CMIP 5. CMIP is this project that asks for help for different institutes around the world to provide their simulations to try to create scenarios for the future. And the IPCC, you may have heard about the COP26 conference in Glasgow, right? This is the CMIP 6 and the report number 6 that they have used to help the conference. And the previous report was number 5. And here are some projections for the future. In red, you see the projections for a more aggressive change in the climate in the future. And as you can see, this red, as time goes by, let's say the year 2100, you can see the band of uncertainty of that red region is much higher than at the beginning, for example, in the year 2050, for example. And as you integrate in time these models, for instance, if you go to the year 2300, you can see there is a large uncertainty. In this case, the global temperature could be anything from 2.3 degrees to 12 degrees, right? So, but where is the true answer there? We don't know. So what people do is, you can see some numbers there. There is a red number, number 12, which means that they've used 12 models to create that region. And before 2100, they used 39 models to create that region. It's just because not everybody has computational resources to run up to the year 2300. So that's why. But it's a large uncertainty. Decision makers need those numbers because they need to make decisions. What should we do with our climate? Should we cut coal, or should we not use fossil fuels anymore? So they need those numbers. Okay. You have in blue and light blue a more business as usual type of thing. You can see the uncertainty is a little bit less. However, there is an uncertainty. In the middle of each of these uncertainty regions, you have a darker color, a line. For example, look at the red part. There is a line going through there. That line basically represents the multi-model mean. So I take all of these models and I average them. So that's what people normally use. But there is a problem with the mean, because the mean doesn't tell the whole story. For instance, some of these models, they share similarities. Instead of developing a whole new model, I can borrow parts from different existing models and create my own model. Because of that, some models, they share some similarities, and we call this climate genealogy. So think about if I have 5 models that share something together, if they give an extreme temperature, when I create the average of all models, these 5 models, they will pull the average towards them, because the mean is sensitive to outliers, for example. And if you have a group that together can influence the mean, they will influence the mean. Let me try to illustrate this in a little while, but before that, just here, I try to classify these models into families just to illustrate the challenge. Here are all of the models used for CMIP5 project. Okay, so if you look at the first column, this is the model. And the second figure here is a continuation because there was not enough space here, okay? So I classify them by continent. And as you can see, for example, in North America, there are many models that come from North America, okay? Many models from Europe, from Asia, etc. So in Europe, when people develop their climate models, they try to, when they test the models, they normally focus, of course, on the global properties if the model is doing well, but they also focus especially on the region of interest, in this case, Europe. So they're going to tune their models so that it produces nice properties globally, but also that produces nice properties for Europe. So there will be some bias because of continent. The same with the atmosphere model. For example, some models, they are created and using the same atmospheric model because it's cheaper to do that way. I just borrow an atmospheric model to construct my own model. And the same with the ocean model. Some of these models, they share the exact same ocean model. And they, of course, they can tune them according to their needs. So there will be, because of these families, some biases, which is the bias due to family. I talked to you about the mean. This is the mean of a wedding. And as you can see, there is an artist called Sullivan, and I borrowed this slide from Doug Nitschke from NCAR. And this artist, he got 100 pictures from weddings, okay? And then he created the average. That's what you see on the right-hand side. That's the average wedding. You can see somebody, you know, like a woman dressed in white and a man and so on. But if you look at the 100 pictures, you can see the details, maybe somebody wearing a military uniform, or somebody that is different, or having, you know, flowers in their hands and so on. There will be differences, but the mean, that's what we see there. So if you have a lot of people wearing white, for example, or dressed with a red flowers in their hands, then the average would have something red from the flowers going on there, right? It's just an example, because this group would influence the mean. And the same with the models. When they share similarities, they will draw the mean towards them. That's what happens considering in terms of statistics. So that's the average weighting. So think about climate now. When you look at the average climate, when you get like 40 models and you average them all, that's what you get, but it doesn't tell the whole story. That's why we need to understand uncertainty. Now, the next question is about how can we model the climate system? This is a huge, huge topic, and it will take us several subjects at university just to go through each of them in detail. But just going through in a few minutes, we remove the equations from this presentation, but in case there is an interest, I can share some other slides or books or that could be of interest. The climate system is extremely complex. As you know, you have a lot of things going on. You have the ocean, but the ocean is not just the first layer of the ocean. You also have the deep ocean. You have currents that are going on there. You have waves that are going on there. You have sea ice also. And then you have some heat exchange. And you have to look at the different time scales of the ocean, because the ocean has a different inertia compared to the atmosphere. So all of that we need to take into account in the models. Then when you look at the land surface, you have many things going on there. You have trees, you have cities, you have pollution, you have snow, and a lot of processes going on at the surface. And the surface is not just the surface. You also have different layers below the surface that the water has to penetrate, that has to go inside, and so on. In addition to that, you have radiation. So you have the sun there trying to heat the surfaces. And they will heat differently because you have the albedo, right? So they will heat completely differently. And that you need to take into account as well. And then you have, of course, the atmosphere, which is complex in itself, looking at the different layers that you can have, clouds being formed, different types of clouds, and these clouds will filter out radiation differently. You have to consider greenhouse gases, etc., etc., etc. If we could simplify a little bit more the figure to the left, that's the figure to the right. It's an oversimplification and extremely simple. But even so, we have to simplify that even further, because we can model that, but it's still a huge, huge thing to model. Maybe you have just to focus on the atmosphere and create just an atmospheric model, or just focus on sea ice, or just focus on the ocean, and so on. And that's what people do. They focus on a specific part, and then they couple all of these elements together. If they cannot couple them together, most of the global models today, they're called Earth system models. They couple many different parts of the climate system. But other models that are simplified, what they do is that they focus on one thing, for example, the atmosphere. And that's, for example, the Worf model. It's an atmospheric model. But how does it do the ocean? Well, it prescribes the ocean. Okay. The Worf model has the possibility for you to activate an ocean model. Yes, very simple ocean model. Yes, you can activate it, couple it. Yes, but normally the Worf model focuses just on the atmosphere, and then you can activate or parameterize things that are not fully modeled there. But that's how we need to do it, because otherwise it becomes too complex. So there's a picture of a global climate model or a general circulation model to the left. And again, we need to look at Earth as a sphere and consider different types of projections to be able to represent Earth. But because, again, we're considering the whole sphere that's to the left, you need to consider the variables like U, V, temperature, etc. We also need to consider the different layers in the atmosphere in the vertical as well. Because of that, global climate models or general circulation models, they're very expensive to run. Some of them are very simple. They can run very fast. They're very simple because of, if you want to make them run fast, you need to make them run at lower resolution. For example, 100 kilometers, 200 kilometers, for instance, then they can run fast. But 100 kilometers, 200 kilometers, they are not in, it's not enough for decision makers, because they have to make a plan about what to do with this neighborhood, what to do with this city, and so on. And because of that, we need information at higher resolution. That's why we have something called the regional climate models, that they use data from the GCM to create their own weather, their own climate in itself, but in a much, much smaller region. We also call them limited area models. The Worf model is this type of model, which is very much used these days, especially in weather prediction centers. Then data from GCMs, because it comes from a higher resolution, can be used in impact models such as water models, food security models, energy models, ecosystem, etc. Even tourism. If I want to know if there's going to be enough snow somewhere in the next season, I can use data from the regional model, not from the global model, because the resolution is not enough to tell me if I'm going to have snow here in my neighborhood or not. Again, projections is something we have to take into account, especially when we're looking at the regional climate models. So Worf is a very flexible model, which allows us to choose different projections, such as Mercator, which is like putting a cylinder around the sphere and then opening that cylinder. The Lambert conformal, which is used much for middle latitudes. It's like putting a cone on top of a sphere and then opening that cone. And then we have the polar stereographic, which cuts the sphere closer to the poles, either the north or south poles. And then we look at that cut in a way. There are different ways of choosing the projection, and by using something that we call scale, because we don't want to, because the problem of using a projection is that it introduces errors also. To minimize those errors, we use something which is called a scale, because we don't want the distortion to be too large. And so we want to make the scale closer to 1. So if you look at these figures to the right, and if you look at the y-axis, that's the scale. If it's closer to 1, that's what you want, because then it means that the distortion, because of the projection, is minimized. So for instance, let's say you live in 60 degrees latitude. And if you look at this plot at 60 degrees latitude, so which projection would you choose? Well, you could choose a polar stereographic if you wanted. You could also choose a Lambert conformal as well. But at 60, I might not choose, for example, a Mercator. Mercator would be more appropriate, for instance, for modeling the tropical regions. So there are ways of making the choice or in a good way. The other thing you have to consider, especially in models such as Worf, which is a limited area model, is the vertical resolution. And this is a very nice illustration from the book by Warner, that he looks at vertical cross sections of vertical velocity, which is omega here. And as you can see, at different levels in the atmosphere, given by pressure in hectopascal in the y-axis. And here it's basically looking at 24-hour simulations of something called conditional symmetric instability. And they're using horizontally 10-kilometer resolution. So basically, figure A and figure B are both using 10-kilometer horizontal resolution. However, figure A is using 75 layers in the vertical, and figure B is using only 25 layers. So what's the difference here? Well, as you can see from figure B, because it uses less vertical layers, it introduces some wiggles that should not be there. Those wiggles are because we are not representing symmetric instability in the atmosphere properly, because we don't have enough layers to represent that properly. So again, if I increase horizontal resolution, I should also increase my vertical resolution. That's the main lesson from here as well. And of course, if I increase vertical resolution, it's going to be more expensive to run the model. So that's another problem that one has to take into account as well. So if I'm producing a weather forecasting for tomorrow and the model is taking too long to run, I will not be able to produce that weather forecasting. So I have to see and make some decisions there. The other thing, especially if you consider some regional models like the Worf model, is that clouds, clouds, they can be in such a small scale that the model, the grid of the model, the resolution of the model is not high enough resolution to represent a cloud. So, which means that cloud, we need to parameterize clouds, meaning that we have to write another model that will try to tell something about the clouds inside a grid point in your model. So should I create a cloud or not? If I create a cloud, how many ice crystals should be there? How many water droplets should be there? And as we integrate the model in time, should the water droplets increase or not? Should we create some ice crystals or not? Should the ice crystals become snow or not? Now, are they heavy enough? Should they fall or not? And if they fall, we need to take into account of that. That's the precipitation that you're measuring then, right, in the model. So all of that has to be taken into account. Extremely complex. So what the Worf model does is that it uses these auxiliary models that are run together with the Worf model, providing information about clouds. So this is called the cloud parameterization. And the cloud microphysics or parameterizations, there is one called the microphysical schemes, which is making decisions about the sorts of things inside the cloud. If I'm gonna create an ice crystal, or if I have water vapor, or if I have a grauple. So, and the schemes can be different. They can have different types of complexity. For example, the scheme C here takes longer to run because it has grauple in addition to many other things. But scheme A is really fast to run because it doesn't have grauple. However, if I'm using scheme A for the tropical regions where I have a lot of grauple going on, I may not be representing the rainfall there in a good way. There is also something called convective parameterization, which is very important for the tropical regions, but also for the summer, where we have convection. Because the Worf model separates rain in two parts. Rain coming from the microphysics, but also rain coming from convective processes, which means that the water warming up and heating and going up, and then creating rain from that process. So Worf separates the rainfall like that. So to get the total rainfall in Worf, we have to sum up rain coming from these two processes. And again, here Worf gives us a number of different parameterization models for convection that we can choose from with different complexities. Another thing that we need to parameterize is turbulence, because turbulence happens at such a small scale that unfortunately, with the resolution that we get from the model, we're not able to represent turbulence properly. So we need these auxiliary models called parameterization again, to be able to say something. For example, should we have turbulent motion now? If we have turbulent motion, how big should this be? How strong should it be? Is it day or is it night? If it's night, we have different processes going on with turbulence. All of that, these schemes or these parameterization schemes, they take that into account and provide the information to the model. So the model is running the atmosphere and so on, and it's getting information about turbulence and about clouds and so on. Another process that the models cannot represent properly is radiation. So that's why we need auxiliary models or parameterization of radiation. So as I'm running the model is also thinking about and looking, okay, oh, there's a cloud here. Oh, how much should we reflect back? How much should go through this cloud? Oh, I have CO2 in the atmosphere, this concentration. So how much should go through? How much should be absorbed? All of that, the radiation schemes, they have to take into account. And then how much energy is actually coming to the surface? And then how much energy is being reflected back. So these auxiliary models for radiation, they make all of these calculations as the model is running. And then there is another type of parameterization called land surface. So for instance, it's raining. Okay, how much of the rain should go inside my soil? And then how much of the rain should run basically from one point to the next and forward? And if the rain goes inside the soil, how deep? So as we are running the model, all of these decisions, they have to be made. And if we have canopy, if we have trees, we have to make decisions as well. Oh, are the trees absorbing the rain or not? How much is it, are they absorbing? How much of the rain not going to the trees or going to the soil? So there are different parameterizations for land surface that can be used also in the Worf model, that and these are running together with the model and providing all of that information and updating everything. As you can see, how complex things can be, but it's an excellent model. Here's an example of one parameterization for land surface. It's a very complex and it's a model on its own. It's called the Worf Hydro. This is a paper that we wrote, actually 2 papers some time back. And this model had just been released and we were testing it for India. And the project in India was about looking at the question of whether India would have enough water resources for the future, because India is dependent on water coming from the Himalayas, right? And also water coming from the monsoon system and so on. And so we wanted to look at the future and seeing, would there be enough water for drinking water? Would there be enough water for food security? Would there be enough water for hydropower as well in India? And so we focused on one basin, and Worf Hydro allowed us to run Worf, but also run this very advanced hydrological model that we could simulate the basin and what was going on with the water in very much detail. And it's just to illustrate how wonderful these models can be. Now, we've discussed this, but why do we need limited area models downscaling? It's because the resolution of global models are not enough. To the left, we have some models used for the IPCC report in different years. For example, in the 1990s, you can see the resolution of global models was just 500 kilometers. And this is Europe, as you can see, Europe, and how it's represented there. Norway, maybe it's just like 4 boxes. Then we have in 1996, then the resolution was 250 kilometers. You can see major improvement at the time. Then we go on to 2001, global models at 180 kilometers. And then 2007, global models at 110 kilometers. Wow, now Norway is many boxes. Greenland is much improved there, Germany and so on. So it improves. And as the year have passed, global models today can be even at very good resolutions, maybe 25 kilometers, for instance. To the right-hand side, we can see that we can use data from global models with bad resolution, and we can run an RCM, a regional climate model, in higher resolution, but then it's a limited area, but provides information at much better resolutions. For example, 10 to 15 kilometers, or even with the Worf model, you can provide information at 1 kilometer. And Worf allows you to run at even higher resolution, just a few meters as well, using something called LES, large eddy simulations. And then data from the RCM can be used in impact models. This is just a simulation that I got from Doug Nitschke from NCAR. To the left this is an animation I'm going to play in a while, but just to explain to you, to the left, you have a global model. You can see the resolution is horrible. In the middle is the global model as well, but zoomed in for the United States. Again, horrible because it's a global model. And to the right, that is the result of getting the data from this box around the US and running a regional climate model in high resolution. And you're going to see how much improved it is here. So as you can see, as the simulation is running, the global model is producing this very coarse data. But to the right, you can see that you can use data from the global model as input to the regional model to produce information at much higher resolution, more detailed. And this is why regional climate models are so useful. And again, this is just the website from the Worf model. It's free of charge. It's a community model, so people can contribute to its development. And it's used in many of the weather prediction centers around the world. In fact, there are people who just use this model and open their own weather prediction centers. And they open their own predictions by just using the Worf model. But the thing you need for the Worf model is you need to install Worf, and you need input data from a global model. So for example, such as the FNL model or GFS model that you can get the data even for free of charge, and you can run Worf and create your own predictions. But you can also reconstruct the past by using reanalysis. So you can get data from reanalysis data and run something in the past. You can also run for the future. You can get data from the IPCC report for the future and use Worf to get information in higher resolution as well. Then you can tell what's going to happen in your own neighborhood in the next decades or so. Just to illustrate here, again, Worf model, for example, that you can get data from a global model and run Worf at 30 kilometers, then 10, 3, 1 kilometer. This is just one example of a setup one could use in Worf. So how Worf does that? Well, the green box is the Worf domain, is the region you're trying to model. And the blue lines and yellow lines are data coming from the global model. So you're just using data from the global models at the boundary of your region of interest. And these data are feeding inside the green area for Worf to produce its own weather or climate. So Worf actually is divided into 5 different programs. One is the Geogrid program, which prepares the data for the region of interest for you. If it's your neighborhood, it's going to prepare everything you need for that. Basically, the topography, it's going to prepare if you have basically everything that you need. Ungrib is going to get the meteorological data from the global model. It's going to ungrib that because normally it's in grib format, and it's going to extract that information and prepare that. MetGrid is going to put these things together, the geographical data for the region of interest plus the atmospheric data. So it's going to prepare that for you for the domain. Then you're done. That's the pre-processing part of Worf called WPS, Worf Preprocessing System. When you're done with that, then you can run something called the RIO. It's going to prepare the data for Worf to be run, which is the last program. And then Worf is going to create the prediction that you want. And again, these are some cheat sheets that Michel has created for us. They illustrate the steps that you need to take to run the model. It looks complicated, but after you learn Worf and get used to running it, it becomes automatic to understand that. And this is part of the course that we have created also, and that we've trained many people to run that. And it's part also of the book about Worf. But installing Worf is not easy. Because of that, we develop different ways of that a person would not need to install Worf. So here's just one example of something we created called eWorf, Worf for educational purposes. This is Worf as is, basically. It is the real model, the real deal. But instead of having you install Worf, we install Worf beforehand and provide you with a file, and which is a virtual hard disk. And you just read that virtual hard disk and Worf is there for you. So you can focus on learning the model and not the burden of installing the model, because it takes a while just to learn how to install the model. And Worf can be run in different ways, even on USB sticks, or even in the cloud using Amazon Web Services, for example. So there are different ways. And we've tried to find throughout the years different ways of making this easier. Just to illustrate why I created this, I remember many years ago, we had projects in Asia, and I was working with some colleagues from NCAR as well on some of these projects, and we had to travel to Bangkok in Thailand, and we were giving a course. There would be 60 people taking the course, and we were installing Worf in like almost 50 computers, and we had to go 1 or 2 days before just to install in each computer. It was a lot of work. And in India, the same. We had to install Worf in so many computers, and this was a burden. So I remember talking with Morgan, and we wrote a paper saying that this doesn't work. I mean, we have to find another way. And that's by using this, we didn't have to install Worf anymore. You just needed a file, and you could start running Worf right out of the box. So that made a lot of life a lot easier. And it was for the first time this had been done, which is the virtualization of the model to make it easier to run and to teach, especially. So just as a short summary, and I think, sorry, Morgan, I went through, I was supposed to speak just for half an hour, but I spoke more than that, but just a short summary here. Global climate models, they are not enough to understand weather or climate. Really, they're not enough because the resolution is too poor, but they're important. Why? Because we can get integrations many years in time. We saw today integrations to 2300, the year 2300, and so on. But then what we can do, we can use limited area models such as Worf to downscale the information to higher resolution. And the Worf model is great. It's free, flexible, it's accessible to everyone. And it also can be adapted to run on any computer system and to produce weather forecasting and even climate predictions. And just some acknowledgements here that I want to say thanks for the teachers taking part of the work that Michel and Lydia and Morgan, they have been doing. And also we thank especially NCAR for making the Worf model free of charge that we can use, but also other centers for making their data free to be used. And that was it from my presentation. Sorry that I spoke more than I should have.
All right, thank you very much, Michael. I think that was great.